I'm Antonio Sala, and in this video we will use the symbolic toolbox in Matlab to solve the differential equations of a spring mass system with some damping when expressed in normalized internal state space representation. In another video, we modeled this mechanical system with this equation in which acceleration was expressed as the second derivative. In here, we will discuss, of course obtaining identical solution, how to address with the symbolic toolbox the normalized representation that officially must be in this form. Only first derivatives at the left-hand side of the equal sign and only linear equations at the right-hand side. Well, in many textbooks we have this expression, but as we will just compute a free response, no input excitation, then this will be 0, so things will be simpler. So how do we write the mass spring equations in this way? Well, instead of writing the acceleration as the second derivative of position, we just need to write the acceleration as the first derivative of the velocity. I mean, this is just a cosmetic rewriting of the equations in this form because mathematicians make nice theoretical developments with matrix A, but from an engineering and physical point of view, at this moment, we will just rewrite the equations saying that acceleration is the first derivative of the speed, so we will not have second derivatives in our expression, but we will actually be writing exactly the same physical model. Here we have it. We will say that velocity is the first derivative of the position with the diff at the left of the equal sign as required in here. And the second equation will say that the acceleration is resulting force divided by mass. Acceleration is the first derivative of the speed, and resulting force divided by mass is, well, the spring term k times position divided by mass, and the friction term b times speed divided by mass. So this is a system of two first-order differential equations, which is of course equivalent to the equations with second derivatives we saw at the start of this video, which we solved in a previous one. So we now store in this ODE sim Matlab variable these two differential equations that, the dsolve command will solve and obtain exactly the same stuff as in the referred video. However, as the A matrix is important in theoretical developments, we will express these two differential equations in vector form, creating a state vector of position and velocity, so its derivative will be 2 times 1, the vector is 2 times 1, and the A matrix will be 2 times 2 size. This is just rewriting these two equations in matrix form, but this is basically the same that you did in high school when you expressed the linear system of equations in matrix form. That's what we are doing at the right-hand side of the equal sign. So we can end up having the same symbolic object if we define this state vector, and if I build an A matrix with these coefficients, because A times x gives me the derivatives of x. Indeed, first equation would be 0 times position plus 1 times velocity, and diff x will be derivative of position in the first equation, derivative of velocity in the second one. So derivative of position is 0 times position plus 1 times speed. So this first equation is of course coincident with this one, so this is an alternate way of writing exactly the same. And indeed, the second equation, in here we'll have the time derivative of velocity, I mean acceleration, and a times x will be, well, k times position divided by m, change sign, b times speed divided by m, change sign. So we end up having this equation of acceleration that, of course, is the same as the one we were writing there. So we were just expressing this operation in matrix form in here. Once you carry out a couple of examples, this is a trivial step. So we may write the ODE typing this code, or we might write the ODE typing this code. Of course, typing it in both ways is not needed. You just may choose one of them, but in here I do it twice for comparison in order to better illustrate what the matrix form representation is actually doing. So at the end, we are having this system of two first-order equations that, of course, dsolve will solve with whatever method it wishes. I need first, again, to replace symbolic variables by the numerical ones. So this is the actual differential equation to be solved, and this is the actual numerical value of the A matrix in such a representation. The eigenvalues of this A matrix are an important thing in theory, if you know it. If you don't, just forget it for the moment being. And if I call the dsolve command, well, it gets me some constants times exponential and sinus and cosinus with 1/5 decay rate and 7/5 oscillation frequency. This is the position in pretty form, and this is the velocity in pretty form, and the initial position and the speed will be, if I substitute time by number 0 in the solution, this velocity, this position, and of course, if I want to obtain a particular solution with initial velocity of 2, initial position of 3, then this is a linear system of equations that lets me compute the values of C1 and C2, but I do not actually need to do that step because dsolve does it for me. If I call the command with the ODE to be solved and I tell him the initial position and initial velocity, then it computes the integration constants and gives me this expression for the position and this expression for the velocity, which of course, if I substitute time in this spring state solution of this particular solution by 0, then I get initial velocity of 2, initial position of 3, as required in my problem statement. Of course, the expression I obtained for the position is totally coincident with the expression for the position we obtained when solving this equation in non-normalized form with second derivatives. Indeed, the position in that case was revising the code. This one exactly equal to the one we obtained here, of course, because it's the same physical system with differential equations written in two different but equivalent ways. Obviously, the plot of position and speed will be the same, and the animation of the movement, how it goes from an initial non-equilibrium condition to a final equilibrium situation, is also identical to that we obtained in the previous video. So we finish with this. Thanks for watching.